a dynamic adaptive mesh refinement and space-time spectral element method for improved capturing of vortical structures in a realistic cryogenic fuel tank. Mark Sussman. Okay, that's actually the name that I had, and I believe you are from the Department of Mathematics of Florida State University. Is that correct?
So this is research to simulate the heat and mass transfer in a cryogenic fuel tank. And so we, over time, we've been developing numerical methods for either fast methods like the nodal methods or I guess direct numerical simulations. So the nodal methods are fast and the direct numerical simulations take a long time, but they model more features, I guess, in the flow field. See, so this is an image of an experiment for a cryogenic fuel tank. And so they have some heaters. They have an inlet at the nozzle, and then they have which has fluid flowing into the tank. And then there's also what is called a liquid acquisition device, which takes fluid out of the tank. And so, okay. I list some of the previous work in this field for simulating the tank with a direct numerical simulation. Most of the previous work, including right up to 2022, many of them used fluent or related, and they use a time stepping. So there's the liquid and the gas in the tank. So since the gas has to be compressible, modeled as a compressible fluid, because when there's phase change, in order to conserve mass, so the density must change in the gas. So many people, they simulate the liquid as an incompressible fluid, and they simulate the gas as a compressible fluid. And since the gas is simulated as a compressible fluid, if one is simulating the complete set of compressible equations, then acoustic waves must be taken into account. So the way they do that is the piezo method, pressure implicit splitting of operators. So this method enables one to take large time steps in the gas. Our question is, so our approach here is, well, if one is taking large time steps in the gas, then perhaps the resolution of the acoustic waves are not going to be accurate if the time steps are larger than the CFL condition needed to meet the stability condition in order to meet the acoustic time step CFL condition. So in the piezo method, they do a semi-implicit method, which enables one to avoid this time step restriction, but then taking large time steps, the method may not accurately capture these acoustic waves. So our approach is to model the gas using a quote-unquote low Mach number approach, where in this work, in the results that I present, we assume that the density is spatially constant and varies only in time. The temperature and the pressure can vary in space and time in the gas. Okay. So, okay, so by doing that, by assuming that the gas is density is spatially constant, we can use a high order method. So we have numerical methods which can go up to any order in space and time, and we study the sensitivity of the results depending on the order of the method. So we have an adaptive mesh refinement, so we can vary the grid resolution, and we also have, we can also vary the temporal resolution, so the order of accuracy and the time discretization. We use adaptive mesh refinement for the in space, and then in time, we use a method called the so-called spectral deferred correction method. Okay, so these are the equations. Again, we use, for more details on the low Mach number approach, I refer, there's many papers. For example, one of the more recent ones, there's a paper by Jialu Tryggvason, for example, but there's many other papers on this approach. Okay. Okay, so anyway, to reiterate, in the liquid, we model it as incompressible, and in the vapor, we're going to model it as compressible, but the density is spatially constant and varies only in time. And then in the bulk, liquid, and vapor regions, we can discretize the equations where we can refine in both space and time, order of accuracy, and also the resolution. So some people call that HP refinement, where we can let the grid size get smaller where needed, and we can also, that's H refinement, and P refinement is where we can vary the order of accuracy. So resolution refinement and order of accuracy refinement. And, all right, and then also we've tested various evaporation models. In all the models that we've tested for the for predicting the rate of evaporation, we assume that the temperature is continuous across the interface, which may not be completely realistic. So there's many recent pieces of work where the temperature might actually been seen experimentally to have a jump at the interface. Okay, so and again, yeah, so with the spectral deferred correction method, given some kind of differential equation, so here I show an ordinary differential equation, but these operators F1, F2, Fm can represent different parts, for example, and they can have space derivatives in them. So, for example, F1 represents advection, F2 is diffusion processes, and F3 can be forces, various body forces, and so on. So given a method which is low order in time, there's a systematic and non-intrusive way to increase the order of accuracy using the so-called spectral deferred correction method. And I give some of the names here. At any rate, I show an outline of the method here, but if one is interested, they can refer to our to our work, we have a previous paper on this, or our earlier work by these people. Okay, so all right, so also, in order to simulate the tank, we developed a means to assimilate the geometry into our code. So we have, we have this adaptive mesh refinement code. We can do H refinement. We can do P refinement. We can increase the order of accuracy in space or time. And then for prescribing the geometry, so what we do is we can prescribe the geometry in a Lagrangian perspective, with nodes and elements, and then we convert them to level set functions, which are convenient for inputting into our simulation code. So boundaries are represented in our code using coupled level set moment of fluid method. So for example, here, this is the Lagrangian representation of an inlet nozzle. Here is Lagrangian representation of the tank. This is after converting these to a level set function. So this is the zero isosurface of the liquid acquisition device. This is a zero isosurface of the inlet nozzle, and then we have the tank. And then we can merge them all together, all the pieces. We also have the heater here. So we have the heaters, inlet nozzles, liquid acquisition device, and the tank, and we can merge them all together. And the simulation code automatically can enforce the proper boundary conditions at all these regions in the geometry. So at the inlet nozzle, we have, we can prescribe an inlet rate, and also for the heater, and so forth and so on. So we have some simulation results here. So for example, we explored tilting the nozzle and looking at how it affects. So the purple is vapor. And so how does the jet of liquid affect the geometry of the vapor, the ullage? So we've run it. This is an image of the grid, of the AMR grid. This is in 3D. So for these simulations, there are certain so for this case where one has a jet impinging a gas bubble, there have been let's see, where there have been papers which introduce this Weber number. And so if the Weber number exceeds a certain cutoff, then it's predicted that the jet will cause the bubble to break. And if it's below a cutoff, the bubble won't break. And so we did some tests, and so far we have agreement with previous results for this. And we, so for example, here I show a comparison on the, this is a axisymmetric simulation. So we only simulate in the R and the Z directions, and we assume axisymmetry. So on the left-hand side, we have a adaptive mesh refinement. Perhaps it's difficult to see. We have adaptive mesh refinement, and then we use a low order method in the liquid and the gas regions. And in this case, on the coarse mesh, the flow is not as accurate. So especially here where one has the jet, here we don't adapt the grid. And if we do a low order method, the jet is diffused and it delays pinch off. Compared to the right-hand side where we did a high order method, and we do capture sharp features with the high order method, even in the coarse grid regions of the grid, right? So, and we show, so here I plot vorticity. So between the, on the left, we had the low order method, on the right, the high order method. This is still work in progress. I think I went fast. I thought this was a 15-minute talk, supposed to be 15 minutes, but anyway, you know, so we have adaptive mesh refinement, we have H refinement, we have, or we can study the sensitivity to the order of accuracy as well. But still, the simulation times are not close to that, for example, for a nodal model. So a nodal model is going to still be much faster than our method. So where are we thinking about going from here? Well, one approach, which I liked, I saw the first speaker talked about the equation-free coupling between the nodal model and a direct numerical simulation. Other approaches that we are thinking about is putting so the libraries that we use for adaptive mesh refinement, which are called AMRX, they have GPU capability. So that's one option. Or we could, another option is there's been recent work on machine learning for subscale models. So we have found that if we have a strategic subscale model for the rate of evaporation and also at the wall where the heater is, then or you know, so we then we can recover reasonably accurate results on coarse meshes. But this is still research in progress here. All right, thank you for your attention.